Good morning everyone. So in the last class we have introduced the concept of Laplace transform. Today we will see how can we use Laplace transform to solve differential equations. But before that we will introduce the concept of shifting formula. So we know that L of f of x is denoted as f of p. Now if I have to compute L of e raised to the power ax f of x, and if I use the definition, then it turns out to be e raised to the power minus p minus ax f of x dx. So instead of e raised to the power minus px, I have p minus a, which means it becomes the Laplace of, or it can be denoted as f of p minus a. So if I have to use the shifting formula, for example, let's say that I have to compute L of e raised to the power ax sin bx. Now recall that what is Laplace of sin bx? It is b by b square plus p square. Yes. And now replace p by p minus a, because I am computing Laplace of e raised to the power ax sin bx. So this is why Laplace of e raised to the power ax sin bx can be written as b by p minus a whole square plus b square. Now let's compute Laplace inverse of 1 by p minus a whole square. So first recall that if there is no a, then what is Laplace inverse of 1 by p square? So Laplace of x is 1 by p square, or x raised to the power n is n factorial by p raised to the power n plus 1. So it means Laplace inverse of 1 by p square is x, and I have to find Laplace inverse of 1 by p minus a whole square. So I multiply x by e raised to the power ax. So Laplace inverse is x and e raised to the power ax. Now again try to compute Laplace of x raised to the power 5 e raised to the power minus 2x. X raised to the power 5, now we know n factorial by p raised to n plus 1. So it is 5 factorial by p raised to the power 6. And e raised to the power minus 2x is there. So p get replaced by p minus a, which means p raised to the power 6 would be p plus 2 raised to the power 6. So it would be 5 factorial by p plus 2 raised to the power 6. Now compute Laplace inverse of 6 by p plus 2 whole square plus 9. For this one, recall the Laplace of sin ax and cos ax. In case of sin ax, it is a by p square plus a square. So it is p plus 2 square. So exponential function would come plus 3 square. So a is 3. So that's why I can write it as Laplace inverse of 3 by p square plus 3 square is sin 3x. If I replace p by p plus 2, e raised to the power minus 2x would come into the picture. And numerator I need 6. So I have 3. So I multiply it by 2. So that's why Laplace inverse of 3 by p plus 2 whole square plus 9 is e raised to the power minus 2x and sin 3x, and this is 2 e raised to the power minus 2x sin 3x. Similarly, try to find Laplace inverse of p plus 2 divided by p square plus 2p plus 5. So if you see the denominator, then it can be written as p plus 1 whole square plus 2 square. Yes. So it means that in the numerator also I need p plus 1. So that's why I should write numerator as p plus 1 plus 1. So I break the numerator as p plus 1 divided by p plus 1 whole square plus 2 square, and 2 by p plus 1 whole square plus 2 square. So now it's straightforward. In both the cases p plus 1 is there, so I have to multiply by e raised to the power minus x. So this becomes e raised to the power minus x and cos 2x. So cos 2x is p by p square plus a square, but instead of p it is p plus 1. So that's why e raised to the power minus x is there. And in this case it is e raised to the power minus x would come and sin 2x. Yes, but the problem here is that it was actually I have to multiply and divide by 1 by 2 because it is p plus 1, but I need 2 here because a by p square plus a square. So this 1 by 2 would be here. Okay, now let's see how can we use Laplace transform to solve a differential equation. So consider that we need to find a particular solution of the following initial value problem, which is y double dash plus a y dash plus b y is equal to f of x, where a and b are constants, y of 0 is y naught and y dash 0 is y 0 dash. Assuming f of x is piecewise continuous and is of exponential order, so that we know that there exists a Laplace transform of f of x. Now if I apply Laplace transform on both the sides, then it becomes ly double dash plus a ly dash plus b ly is equal to l f of x. Till now we do not know what is L of y dash and L of y double dash. F of x is known, so L of f of x can be found. So let's try to find by yourself what is L of y dash using the definition. So it comes out to be 0 to infinite e raised to power minus px y dash dx. I consider e raised to power minus px as first function, y dash as second function, and solve it further. So it turns out to be this. If you see the second term, then it is simply p and L of y. But in the first term, when y is 0, it becomes y of 0, which is given. And when x tends to infinity, this term becomes 0. So we have to assume that p is greater than 0. And in that case, I can write that L of y dash is equal to minus y of 0 plus p L of y. So this we need to remember. We can use it directly. Now L of y double dash, compute L of y double dash. For computing L of y double dash, if you use the definition, you may kill a lot of your time. So better is to use L of y dash which we have computed, because you can write y double dash as y dash and dash. So L of y double dash is L of y dash and dash. It means in equation 3 you replace y by y dash. So that gives you L of y double dash as p L y dash minus y dash naught. Ly dash has already been computed, which is p L of y minus y naught. So that's why you get L of y double dash as p square L of y minus p y naught minus y dash naught. Now all the calculations have been done. Substitute all these values into equation 2 and then you simplify it for L of y. And now if you take Laplace inverse on both the sides, then you will get y of x. So we are looking for the particular solution. It means we are looking for y of x. Things would be clear once you see few examples. So let us say that using Laplace transform, we need to solve the differential equation y double dash plus 4y is equal to 4x, y naught is 1 and y dash naught is 5. Apply Laplace transform on both the sides. Recall that L of y double dash is p square L of y minus p y naught minus y naught dash. Substitute the values. Now substitute the value of y naught as 1, y naught dash as 5. Take L of y common and take other terms on the other side. Also remember that on the right hand side I have 4x, so Laplace of x is 1 by p square. So I keep L of y on this side, I take p plus 5 on that side, and p square plus 4 is common to L of y. That's why it becomes p square plus 4 L of y and 4 by p square plus p plus 5. It means my L of y is p by p square plus 2 square, 5 by p square plus 2 square, and 4 by p square and p square plus 4. Now I do not know Laplace inverse of 4 by p square and p square plus 4. So I further simplify it, and you can see that it can be easily written as 1 by p square minus 1 by p square plus 4. Now p square plus 4 can be adjusted here, and that's why your y is L inverse of p by p square plus 2 square plus L inverse of 4 by p square plus 2 square plus L inverse of 1 by p square. So the first term is p by p square plus a square, so it is cos 2x. Next one has a 2 extra because a by p square plus a square, so 2 sine 2x, and the last one is simply x, so which is the particular solution of the given differential equation. Similarly, let's try one more question. Y double dash plus 2y dash plus 5y is equal to 3 e raised to the power minus x sine x. So we know the Laplace of e raised to the power ax and sine x. Exponential function is there, so p get replaced by p minus a. And if I substitute the value of Ly double dash, Ly dash, y naught is 0, y dash naught is 3, and do this simplification by yourself, you will observe that you will get L of y as follows. So L of y is 3 by, and this can be written as p plus 1 whole square plus 2 square plus 3 p square plus 2p plus 2 and p square plus 2p plus 5. It need to be simplified, so p square plus 2p plus 5, and it can be written as this. You can verify by yourself. Now if I take these two terms together, then it simply becomes, the first term is 3 minus 1, which is 2, so 2 by p plus 1 whole square plus 2 square, plus next term is p plus 1 whole square plus 1 square. It means y of x is Laplace inverse of these two terms, so e raised to the power minus x would come with both the terms. The first term is giving you sine 2x and the next one is giving sine x. So you can see that it's quite quick and easy to find a particular solution using Laplace transform. Now there is a result which says that Laplace of 0 to x f of x dx is equal to f of p by p. It's quite easy to prove. You can try by yourself, spend some time. So let's take 0 to x f of x dx as g of x and differentiate both the sides. So it becomes g dash x is equal to f of x by fundamental theorem of calculus. Now apply Laplace transform on both the sides. So we know that we have just computed the Laplace of y dash, so therefore we can compute the Laplace of g dash x, which is p times Laplace of g of x minus, if I apply Laplace formula, so p times Laplace of g of x minus g naught is equal to f of p, because Laplace of f of x is f of p. Now what is g naught? G of x is integration from 0 to x, so g naught is integration from 0 to 0, both the limits are same, therefore it is 0, and therefore Laplace of g of x is f of p by p. So this is what need to be proved. So proof is easy, but the important is the result. We can use this result sometimes to find the Laplace of some particular function or Laplace inverse of some particular function. For example, let's assume that I need to find the Laplace inverse of 1 by p square plus 1. In this case, I can use the partial fraction and then solve it. But we have just seen that Laplace of 0 to x f of x dx is f of p by p. So here again 1 by p is there. It means if I can find the function f of x, which is Laplace inverse of 1 by p square plus 1, then I can easily find Laplace inverse of 1 by p square plus 1. So to find the f of x is Laplace inverse of 1 by p square plus 1, which is simply sin x. It means Laplace inverse of 1 by p square plus 1 is equal to integration of sin x from 0 to x, which comes out to be 1 minus cos x. So let's try the last question, which says that solve the differential equation y dash plus 4y plus 5 0 to x y dx is equal to e raised to the power minus x. Again, if I have to use the Laplace transform, apply it on both the sides. So it becomes Laplace of y dash plus 4L of y plus 5L of 0 to x y dx. Yes, L of y dash I already know. I just have to see what would be L of 0 to x y dx. Yes, so it would be there, it used to be L of f of x by p, because f of p is L of f of x. Instead of f of x, if I have y, it becomes L of y by p. So this is how it looks like. And now it becomes, if you simplify it, then rest is simple. You have to use the partial fraction. And if you use the partial fraction, this is how it turns out to be. First term is simple, minus 1 by 2, 1 by p plus 1. And next is p plus 5 by p square plus 4p plus 1. If you see the denominator, then it is p plus 2 whole square plus 1. So p plus 2 is there. It means in the numerator also I need p plus 2. So I should write numerator as p plus 2 plus 3. So if you write it like this, then your numerator would be minus, this is 1 by 2, and 1 by p plus 1 plus 1 by 2 p plus 2 by p plus 2 whole square plus 1, and 3 by 2 p plus 2 whole square plus 1. If you take Laplace inverse on both the sides, the first term is minus 1 by 2, it is 1 by p. So this is Laplace of 1, but p plus 1 is their exponential function, so e raised to the power minus x. Then e raised to the power minus 2x cos x, and e raised to the power minus 2x sin x. So that's all from today's class. Thank you.